Okay then. As we'll see as we go along, and I'll probably repeat myself again, what the Dsp Lab in a box is concerned with is strengthening students' understanding of DSP concepts. It doesn't delve so much as some of the other Lab in a boxes into the hardware specifics of the ARM processor, and in this case the NXP's processor board and the Embedded Artist's experimenter board. So here's an outline of what I'm going to do. I've kind of given you this already. I'm going to try and describe what the Dsp Lab in a box is, give you a bit of background, particularly about myself on hands-on DSP teaching, and talk about hardware platform options, and then we're going to home in on the NXP hardware platform that we've got on the bench in front of us today, and which is really superb. And then we're going to go into some example program demonstrations from the Lab in the box. At that point we can be a little bit flexible as to how many we actually get through. And then finally, actually in this case Khaled has already introduced how you can get in touch with the ARM University program and how you could get your hands on the Dsp Lab in a box. Again, with the introduction from the other speakers, we've already seen the Lab in a Box is an ARM University program concept. It's a resource that is being donated to universities by the ARM University program, and you get hardware, you get a seed collection of boards. The hope is that you'll go on and expand your activities and buy more, but you'll get actual hardware donated free of charge from the university program. You'll also get lecture PowerPoints, you'll also get lab experiment instructions, and you'll get code that will run on the board to do those labs, and you'll also get quizzes, tutorial questions, and so on and so forth. Now the Dsp Lab in a box follows this pattern. Its aim is to enhance DSP teaching by introducing a hands-on element, and I say hands-on, you could say it's test equipment on. It's doing actual experiments with electrical signals, in this case representing audio, in the electrical engineering lab in a university and in real time. We're not just crunching numbers and looking at the results later. All of these experiments are going to process audio in real time in order to try and strengthen students' understanding of the underlying concepts. And pretty obviously from what's gone before, it's based on using an ARM Cortex-M4 processor, more of which in a few minutes. So what is digital signal processing? Well, it's rather unfair of me to toss that question to you because, as we'll see in a moment even, I'm going to suggest several answers to that, and at the moment you don't quite know what wavelength I'm operating on. So don't worry, I'm not going to ask you that question, I'm going to answer it for you. I think this is why we're here today. It's an important and fundamental element of many electrical engineering programs today. Lots and lots of electrical engineering courses, degree programs rather, are including DSP these days. Now, another answer that I hope is relevant to us here today is DSP tends to be a comparatively mathematical and theoretical topic, and we can't really get away from that. If we're teaching DSP in a university, we're going to do a lot of maths in the lectures. I don't actually see a way around that. However, as we'll see, hopefully, the Dsp Lab in a box is going to help people to get into the lab as well in order to see real-time demonstrations of what we've been writing on the board in mathematical form. That really is that is probably the most fundamental idea behind this Dsp Lab in a box. Equally, here's another answer, possible answer to what is digital signal processing. Well, if you ignore the parts in the Pascal-style comments here, then processing of sampled and quantized signals is a bit of a cop-out, because that's actually just saying what digital signal processing obviously is. However, if we're teaching digital signal processing as part of an electrical engineering course, and I can check with you later whether you're actually teaching electrical engineering, but my point I was trying to make here was that typically as electrical engineers we're going to be interested in digital signal processing where the signals or the numbers inside our system are representing physical quantities. Because of course digital signal processing could be thought of as, it's all numbers in the end, and that might represent financial data, or it might represent some other kind of data that's being collected on some topic or other. It's all just sums in the end, but as electrical engineers, typically those numbers are going to be representing physical quantities gathered through transducers into digital processing hardware, which might be a processor, or it might be an FPGA, or it might be dedicated hardware, whatever. And also, as electrical engineers, very often, as opposed to people who are working in financial markets, say, we're interested in real-time processing of these signals. I'm kind of beating on about the same thing here, but the idea of the hands-on laboratory experiments that make up the DSP Lab in a box is that we're bridging between a number of different topic areas. And although the DSP Lab in a box includes lecture slides and it includes suggested laboratory experiments, it gives you the instructions on how to run some of the example software that we have here, and hopefully that's presented in quite a useful way. The DSP Lab in a box is a resource. It's going to give you the capability to process signals in real time on this NXP hardware, and it's up to you if you want to adapt it or adjust it to your own requirements. And some of the directions that you might go in is to emphasize or to strengthen the parts of the activities that are concerned with mathematical theory, electrical engineering, or even the use of microprocessors. I'm going to give you some demonstrations here, and the key part of these is going to be the illustration of digital signal processing concepts. But equally, we've got this board in front of us. You have all the source code, you have all the tools in the MDK ARM development environment that you can go in and look at programming styles, you can look at debugging the programs, you can look at the detail of real-time performance and so on. So you might want to go in that direction in your classes. And if you carry out any of these DSP Lab in a box activities, then your students are going to be gaining experience in these type of areas. Okay, well, some of you have said that you are already teaching, or maybe thinking of teaching, digital signal processing. This is a pretty straightforward and conventional list of topics that are covered in digital signal processing. Okay, we're not at the bleeding edge of research here. However, every year, remember, we've got more students coming through the system. This is to state the blindingly obvious, really, and they haven't studied DSP before, and these really are the fundamental topics. They've been like that for a while, but for good reason. Okay, a bit of background on hands-on digital signal processing. I've been teaching digital signal processing at Heriot-Watt University in Edinburgh for about 13 or 14 years now, ever since my head of department called me into the office and told me to do it. And right from the start, I felt that I'd like to do something more than just give mathematical lectures. I'd like to get the students into the laboratory as well, and to do some actual electrical engineering experiments. And so I got into contact with a professor in the US called Ralph Chassing, and it turned out that he'd written a book on doing so-called hands-on digital signal processing experiments in a laboratory, and he was using some Texas Instruments equipment. Anyway, I got in touch with him and we began to collaborate on expanding the range of experiments that he or we were doing in our laboratories. And as Texas Instruments at that stage were bringing out generation after generation of new digital signal processing hardware, and with it generation after generation of low-cost digital signal processing development kits, so Ralph and my books tracked this. Now at this stage on these ones, I was developing the actual laboratory experiments, then by the time we got to here, I'm actually listed as a co-author rather than just acknowledged inside the book. And then we got to the most recent book of all. Sadly, Ralph passed away in 2005, and it's actually these two books here have come out since then. And as we'll see today, I'm really taking this a little bit further. In fact, I'll talk about that in a moment. So what we were looking at was doing laboratory experiments, and the idea, or sorry, the medium, if that's the right word, that we used was audio processing. Because around the world, we'll see in a moment, the kind of laboratory equipment that can generate, that can display, that can analyse, that can use audio frequency signals is pretty much ubiquitous. You don't really need to have any specialised equipment. This is equipment that you'd have in any university electrical engineering department. So this is a picture, admittedly 2006, and things have moved on a little bit, but this was my teaching laboratory back then, and as you can see, the basic tools that we were using was a PC in order to develop the DSP code. You can see, I'll leave it to you to spot these items in the photograph. There's a digital signal processing development kit hardware on the bench there. There are some lab instructions telling the students what sort of things I want them to try and do, and then there's a pretty standard oscilloscope that can cope with audio frequency signals and above. We'll see, we're also going to look at some digital signals as well on an oscilloscope, and there's an audio frequency signal generator. And as I say, you can find this type of equipment around the world. I've gone on the road, so to speak, and visited universities, for example, here in China. I've just taken the DSP boards, the hardware. In our case, we'd be talking about this, although I'll say more in a minute. With this kit, as we'll see shortly, you could pretty much expect the universities to have got them for themselves. But if I just took the boards, as I say, any self-respecting university electrical engineering department is going to have PCs, scopes, signal generators, and so on. And this is another workshop that I ran. This was a 2-day workshop that I ran in a university in India. I could bore you with lots of other holiday snapshots, but you'll be glad to know I won't. Right, the heart of what I use in the DSP Lab in a Box experiments is a system that looks like this, as you might probably have guessed. Ultimately, what we're interested in doing is processing analog audio signals, well, albeit represented as continuous time voltage waveforms. So they've been transduced, taken from a microphone or from a player or whatever. But the system that we've got on our hardware kit is essentially this. At the centre of that was a digital signal processor. We'll go over this bit quite quickly, just in case anyone is in any question about this. A digital signal processor, especially if you went back 5 years, this was maybe a bit of an esoteric bit of kit. People would go, they're a bit tricky, aren't they, digital signal processors? They're just specialised microprocessors, as I'm sure you're quite aware. How are they specialised? Well, these are the type of things. There's no strict definition, of course, of what is a digital signal processor and what is not. But these are some of the features that you typically find in what a manufacturer refers to as a digital signal processor. And there's some reason as to why I'm mentioning some of these, particularly because of the format of the most common digital signal processing algorithms, filters and FFTs. Both of these are based through the use of convolution and correlation. They're based on sums of products. And that's the reason why digital signal processors typically have separate program and data memory buses, at least 2. And of course, that's what we call a Harvard architecture. And they typically have single cycle multiply accumulate in their ALUs. And the reason for that is if you have more than one memory subsystem, you can fetch 2 operands in one instruction cycle. And typically you want to fetch 2 operands. These would be the operands in a multiply accumulate operation, which of course is part of the sum of products in a convolution or a correlation sum. And then if you can multiply and accumulate those two operands in one cycle in your ALU, then you're in business for digital signal processing in real time. And then there are some other typical features listed there. Now let's go back a little bit in history. Maybe about 10 years ago, a low-cost digital signal processing development kit looked like this. In fact, I've been using these I used these for about 8 years in my university. This is a Texas Instruments board, and it's got actually an extremely powerful C6 series digital signal processor on it. It has analog audio I/O on it here, so I could get audio signals in and out. It's got an analog to digital and digital to analog converter, a codec on the board as well, obviously, and that suited my purposes very well. These things cost about $400 a pop, although in their defense, TI used to have a pretty generous university donation scheme. Latterly, my most recent book, mainly at TI's behest, used an OMAP L138 processor-based board, and they first came out with this one that cost $300, and then they moved on to what they called the low-cost development kit, and you can still get this from TI at under $200, although you had to buy a separate JTAG emulator if you wanted to program this board, so there was a little bit of extra expense there. But then came ARM Cortex-M4, and ARM Cortex-M4 was, as far as I was concerned, well, okay, in terms of processors that I was aware of, and I'm unaware probably of lots and lots of processors, but I became aware of the ARM Cortex-M4. And as I'm stating on this slide here, this combines digital signal processing and more standard microcontroller features. It has a Harvard architecture. It has a floating, in some cases, some variants, including the one that we're using here. It has a floating point ALU that has a hardware multiply accumulator in it. So it's pretty much capable of doing real-time audio processing. That is the bottom line there. To give you a little bit of a cringe-worthy anecdote here, I first became aware of this, I can't take all the credit, a colleague of mine emailed me in early 2013, and he said, "Donald, guess what? You could do all your real-time DSP experiments on an ARM Cortex-M4. Forget about Texas Instruments DSP, you can do it all on an ARM Cortex-M4. So this is a cringeworthy bit, but I'll go through it anyway. I did two things. First of all, I emailed him back, of course, and said, "Robert, a C6 DSP from TI would eat an ARM Cortex-M4 for breakfast." And the other thing I did was I rushed out and I bought a $15 ARM Cortex-M4 development kit and ported all my DSP experiments onto it, and bingo, there we were. Of course, I've missed out a couple of steps there. I had to build an audio interface for that inexpensive Cortex-M4 development kit. But the thing is that now you can get that audio interface on the Embedded Artists experiment board. So here we are now at the hardware that we're going to use today, and it really is pretty much a step change from those low-cost digital signal processing platforms that I was using before. We're now looking, and I'm not absolutely sure how accurate this is. There are discounts for universities, and there's obviously a donation scheme of seed hardware from the ARM University program, but we may be looking at a price of around $90 US for this package. That's both of these boards. The Quick Start board from NXP, that's the red board there, and the larger green board, of course, is the Embedded Artists Experiment base board. And in fact, Brendan and Anders have already run you through in quite a bit of detail what the features of these are, and there are a lot of features. I'm desperately hoping that the numbers and stuff that I put down the left-hand side here are the same as Anders and Brendan gave you, but I think that they're not far off. As they mentioned, we've got 128 megahertz clock, ARM Cortex-M4F, that's F for floating point, on there. It's got plenty of RAM and other memory in order to carry out the Dsp Lab in a box experiments. As Khaled has already covered here, there's a great deal more that you can do with this hardware combination than simply run the Dsp Lab in a box. You can run, as he was mentioning, at least 3 other ARM University program Lab in a boxes, and I'm sure there are plenty of things that ARM University program has lined up in the future, or that you can develop for yourselves that you can use with this. So there it is. I've only bothered to list some of the features down here. These are for the embedded artists board that I'm actually using. If you were really paying attention earlier on, I showed you that one of the DSP boards from TI, I indicated the audio interface. Well, we've got just exactly the same capability here on the NXP experiment baseboard, so we can get signals in and out, and we're going to use them. So again, Khaled actually showed you a slide, and this is a resume of what are the various different topic areas covered by the Dsp Lab in a box, and of course they coincide with what I earlier called the fundamental areas of digital signal processing. And we're getting now onto the point where I'm going to try and do some live demonstrations, and where possibly everything is going to fall apart. Also, I think we can be fairly informal here. If you've got any questions, if you want to ask anything about any of these as we go along, then please do. So we've got the board here, and at the moment we've actually got the setup that's drawn on here. Now, we're not actually going to run the loop program yet. I'll do that. I'm going to do this in real time. I'll start up the NDK ARM development environment, and we'll look at loading and running different example programs. But we have got the microphone connected, and we have got the loudspeaker here connected, and I've just noticed my first deliberate mistake here. It says headset there, it should say microphone in, but headset is combined microphone and earphones, and never mind. Now, one of the nice things, it's a very little thing and it's not exactly unique to this hardware, but what's really nice, I think, about this hardware here is that the Cortex-M4 processor has onboard flash. Actually, as was it, I think it was Brendan was mentioning, you've got megabytes of off-board flash on this board. You're nodding, is that correct? I think it's serially accessed. I'm actually not using that for any of these DSP experiments. But anyway, the point is that all these little experiments that make up the Dsp Lab in a box, you program the processor to do something, and it keeps that program in flash. So when I plug in the USB cable, and that's another nice thing about these compared with earlier hardware, it's all powered off the USB. You don't need a separate AC to DC adapter and so on. Once I plug this in, it will remember the previous program that was loaded and run, and fascinatingly, that should just be a little bit of an echo. I'm glad there's not too many people here, because these loudspeakers are rather quieter than I was hoping. Anyway, that's in there. So the thing is alive, as you can see there. In fact, we'll just do something even simpler than that. In a moment, we'll do that loop-through program. I plugged this in, and you can actually see it's come up and told us that it's an mbed-enabled device. That's what that's about, but we're not actually going to use that. What I'm going to do is I'm going to bring up, this is the MDK ARM development environment window, and basically over here we've got projects, and then we have lots of windows that I'm not going to talk about. This is just a text editing window where we can have a look at source code, but that's not massively relevant to us here. Here are all the parts of the project, and the emphasis or the focus in the DSP Lab in a Box experiments is on some short C programs that implement different things. Now, I'll get rid of this echo program. As I say, this is all live demo, and I will add into our project. You don't need to know exactly what I'm doing here, but I'm going to add in a program called loop.
Click add.
It's okay, it has added it. And this is the sort of thing that students will be doing in the lab. I've put in a particular source file. We're going to have a look at it in a moment. And now I've compiled and linked, and we'll do this before we look at the code. We will download that onto our processor. While the processor is not actually running a distinct program, there's the possibility that you get noise coming out through the codec. Basically, it's undefined what's going on at the moment. It's come up with a window here, and that's indicating that all of, well, it's not indicating, it's it's saying that I'm using the free version of MDK ARM here, which I am, and which actually, I'm not going to prove it, but I'm going to tell you that you can run all of the DSP Lab in a Box experiments using the free version of MDK ARM. And seriously, it's simple to download it from the web and get it going, install it and get it going very quickly. However, if you get a donation from the ARM University program, you won't have the bother of these little windows here. You'll actually get licenses for the absolutely industrial strength version of MDK ARM. Anyway, so now we'll just run this program, and the system, you can just about make out that something is happening. The system is live. We've got signals coming in from the microphone and coming out to there. We're not doing any processing as such, but we'll go back. So this is meant to be a block diagram representation of what's going on here. We've got the microphone, and the signal from that is being converted to digital by the analog to digital converter. Effectively, what our loop program is doing is acting like a piece of wire straight through to the digital to analog converter, so our signal was passing through there. What is the program that does that? I'm not going to show you loads of code here this morning. It's almost afternoon, because that's not terribly interesting. This is one of only about 3 slides that have got any code listings on them. But this is to give you a flavour of how these real-time programs work. We've got 3 areas in this code here. Obviously there's some stuff behind the scenes that's been hidden away, but this is the type of thing that the students are going to see. Up at the top we've got a little bit of preprocessor commands and declarations. Down at the bottom we've got the main function, and one of the most important things here is audio init. So that's hiding some of the low-level detail from the students, if that's what you want to do. All the source code for this is made available to you as part of the DSP Lab in a Box. It's not proprietary or secret. You can see here that we pass it a few parameters. We have a few choices that we can make. We can choose the sampling frequency. In this case, it's 8,000 Hertz. I think I was running that at 48,000 actually. We can see in a minute. These experiments, a lot of them run at 8 kilohertz, particularly when we do some more complicated processing. But some of the simpler programs run at 48 kilohertz, and certainly you have that capability on the codec on the embedded artist's board. It can run up to 48,000 kilohertz sampling, which of course is high CD anyway quality audio. We can choose where our input is coming in from. In fact, this is not exactly the code that I was running. Wheels are coming off here a little bit. You can see here I've chosen line in. Actually, I was using microphone in just then, and so on and so forth. But then we go into, moving on very quickly here, we go into an endless while loop. We're doing sample by sample interrupt based I/O here. At 8 kilohertz sampling rate, that means we're going to be having, the codec is converting 8,000 times a second, and it's going to generate an interrupt 8,000 times a second. And then when we have interrupts, we're going to do our processing. In this case, there's no processing at all inside an interrupt service routine there. And we do give these interrupt service routine source up front to the students, because what most of the other experiments does is they put the processing in here. Now, for purists among you, or maybe that should mean anyone who knows what they're doing among you, you might recoil at the idea of putting much processing inside this hardware interrupt service routine. However, remember, we're just doing very simple example programs here. We haven't got any other threads or anything running on our processor, so I think we can get away with it. Also, software engineering is not really the focus of the DSP Lab in a box. So there's no getting away from it. Most of these examples, what they're doing is they're putting digital signal processing code inside a hardware interrupt service routine.
Could you use the wait for interrupt instruction there, or would you gauge it up on the...
Sorry, could you run that part?
There's a wait for interrupt instruction in the ARM. So you could put it in sleep mode.
Yeah.
Because
I guess you could do that, yeah.
Interrupt. Does that give you a jitter on the sampling point? I don't know, I'm not
Basically,
sure.
I haven't tried it, so I haven't gone there. So I don't know. What I was going to say here was that there are basically two groups of example programs. This one, we're doing it sample by sample interrupt. The other way is to use DMA to get blocks of data from the codec, to and from the codec, between the codec and the processor, and that's covered as well. Now, the basic structure of a program there looks a little bit different from this, but we do that as well, and that's covered in some of the exercises. Another thing that we can do is we can use GPIO pins for timing measurements, and that's built into a lot of these example programs. Now here we're not doing any processing worth talking about that we want to measure the execution of time of. So actually that loop program, I'm not going to fix it up with the oscilloscope here, you'll see in a moment. We were in our interrupt service routine, we're toggling one of the GPIO pins, and so that's giving an indication that we are doing sample by sample processing at 8 kilohertz. And for those of you who can't imagine what a 24 is, that's at 8 kilohertz. That was running at 48 kilohertz. So if we toggle, we get a 24 kilohertz square wave. And for those, I was going to say, for those of you who can't imagine what that looks like, there's a picture of a 24 kilohertz square wave on the GPIO pin. So if you've got a scope, and I'm not going to use it for that, but I've got a scope here, we'll get onto that later, you can just go onto some of these headers here, and, well, in this case, go onto the correct header, and you'll see a signal. And you can set these pins, and you can reset these pins. And I use that in some of the DSP Lab in a Box experiments in order to see how long it took to implement a filter or to calculate an FFT of a block of data. So it's rough and ready. There are capabilities within the MDK ARM development environment to simulate the processor and to do processor cycle counts in there. So that's an alternative way of calculating it, but execution times, but this is a rough and ready method that's used in several of the experiments.